welcome everyone. This is actually week 5 of like data science. It's like week 5 of the data science course over here. Lectures and everything like that, interactive lectures. And we're going to be going over basically analytic base tables and data quality reports. And so I didn't include the definition here, but like we're going to go through this and make sure that you have you run all your imports. Oh, goodness.
Don't even bother.
Anyway. Okay. Yeah, just run all your imports, and I have all the like different like some of the different. Huh? Okay.
That gives you the data.
That's okay. Yeah, but definitely make sure to run the second cell as well. And so we're gonna start off like with
Actually, before we do that though,
Yeah.
sorry, but before we do that, just everyone make sure once you run that second cell, you have some sort of file in here that should say big files. Ours is a little jacked up, but it should just have a folder in it called CSV data. If it doesn't look like that, please tell me like now. Otherwise, we're going to proceed. Assuming it looks good for everybody. All right, cool. Moving on. Back to the standard show.
all right, thanks for that.
No worries.
Anyways, yeah, so we're gonna start off okay, over here we're gonna start off with analytic base tables. And basically analytic base tables basically where all our data is aggregated together. All the data we're gonna be working with or whatever sort of like machine learning model that we're gonna be using or any sort of other algorithms. And so I just include over here just like some of the functions that we'll be using, which I mean we're gonna be going through. But basically you might really want to write this in your little comment, like where it says description. If it's not already included, it probably isn't because I never removed all those. Yeah, so basically, like this function saves all the file strings ending with CSV. So you can look at it like you actually like look at like the internals of the function, and you can see like it saves all the files ending with CSV in a dictionary to like a variable all files, and the collection iterates through each of the elements being used as a file name. For the function pd.readCSV, and basically doing that generates a data frame, and we append that data frame into this list that's that we call data frames, and we're going to make a data like a merged data frame basically, or DDF merge, which is going to utilize this lambda function to like literally basically merge each data frame to the next data frame. And we're doing this outer merge. So let's say in the description you just say like that this function saves all the file strings ending with .csv in a directory to variables to a variable all variables collections iterate through, and it's appended to the variable data frames, and then that it's appended to the variable data frames, and then we use the lambda function to basically iterate through and merge each data frame. And your arguments is basically just like the path address, which is a string, and then you have your outputs, which is a merge df, which is going to contain the mutually exclusive data, mutually exclusive numerical data for several data sources. It may like it's not specifically like looking for numerical data, but this is sort of the data that we're working with. But basically, you can just say it's the mutually exclusive data from several data sources. All right, so I'm just gonna run this file. Run this cell, and we're gonna run this so we actually want to like see what we get like once we actually import all of our get all of our data from the CSV data. And we're going to get the merge df head. So this is what happens like after all the data frames are merged together, they're outer merged, which brings up their mutually exclusive data, and they're merged based on like they have some they basically have a similar data in that they have like UHF-42 and incident address borough, but like all these other columns, and they also have they share date received, but all these other individual columns are from these individual data sets or CSV files merged put together. Now going forward, we just sort of want to like check our data frame, just like see some attributes about it, like see how many rows and columns. And we can just use the shape. We can use this function formally. And similarly, we're going to check the data types that are within the data frame, because some of these like names are a little bit, they're pretty long, like incident address borough, date received. Maybe you can like bring that down so that we can just say maybe just borough. and date received. We only have years here, so we can just say year. And that's what we're going to do on this cell over here as we do the complaints. This is called the complaints data frame, by the way, because this is basically this is the count of complaints in New York City boroughs for every year. So this is just making sure you guys know why it's called complaints DF. And so we change instead borough to borough. We're going to change date received into year. And we also, what we want to do is also change the type of the data type of year. So after we see over here, the data type of year is N64. So we want to change that because we're not going to do any mathematical operations on this. So we're just like going to keep it as a string. And so we do that over here. We change year to as type string str. So we do that, and we see the output. It's like creating now year is an object, and yeah, we have borough over here and year. So that's great. Just cleans up the naming convention a little bit better. Makes it a little bit more concise. And now we just want to see that everything's doing well, it's running well. The names have changed. So that's awesome. That's pretty basic stuff. Now we want to get into, let's say, looking into the data quality and looking into some attributes about how the data relates to other data within the set. And so to sort of just visually see that, we can use this Seaborn pair plot. And over here, borough is used for hue, which is basically distinguishing each individual, let's say, group of data by color. So all the boroughs will be distinguished by a certain color, and you can sort of see their interaction with other variables as this generates. And what this is going to help us sort of intuit is basically see relations between data. So linear relations or exponential relations. So maybe we would look over here and we would see there seems to be a certain linear relation with maybe these Brooklyn with so we look at sewage odor counts, and we see sewage leak counts, and then we see as we can look at, let's say, just the orange dots which indicate Brooklyn, and as we go as we increase sewage leak counts, we can sewage odor, sewage odors. Wait, is that both sewage leak? No, so sorry, this is asbestos counts versus sewage leak counts. So as you increase, let's say, asbestos count, sewage leak counts, you see there's an increase, some sort of correlation with asbestos counts. Similarly, with sewage odor counts, as you increase sewage leak counts, you see some sort of linear correlation with the sewage odor counts. And this is again just focusing on Brooklyn, just as as an example. But you can also just look through the other data and see there's some sort of relationship over here as well. You can see sewage odor count, sewage count with asbestos count. Again, over here it shows that sort of relationship. But this is just helping us see what potential data within what particular features within our data set may have some sort of significant correlation that we can use for a model later on. And you can also just see that numerically by using complaints df.core, basically the .core function here. And you can just run this cell, and it gives you the correlation of each data with respect to another feature. Well, each feature with respect to another feature. So this is sort of just gives us a bit of the lay of the land of our data, just seeing how each feature correlates with each other, see that visually, see that numerically. It's just sort of helpful. When it comes to, let's say, what sort of transformation that we want to make on our data set to improve correlated values, which will be used as predictive features for models going down the line. So what we first want to do, part of our data quality report, the first part of our data quality report is basically seeing the features or the characteristics. The characteristics of our continuous data, and that's going to be our float data. And so we're going to be using this function over here, continuous quality. You can see over here, there's the description of the function over here. Creates a data frame containing data quality metrics for each float 64 feature. So those are the features that we actually care about, since those are the features that we would be using for any sort of model or algorithm. And over here, you can just see arguments frame and output. It's going to be a continuous data frame. The continuous data frame, data frame, which is our continuous data quality reports can contain like the count, contain the count of percent missing, cardinality. Cardinality is basically just the amount of like unique values within the feature. And have our min, first quartile, median, third quartile, max, standard deviation, all that good stuff. And so we're gonna run this function and see what it gives us. Okay, so this is gonna show us something about our data here without having to, manually look through it. So we're gonna see like, okay, what are like the amount of counts that we have for gas counts. Okay, this stuff is, I mean, it's important, but it's not necessarily like our most pertinent feature, like characteristic that we care about. What we do really care about is this here, missing data. So you may want to like note this somewhere, but like if you have data, if you have missing data of around like around 60%, you want to take out that feature. Because it's not really going to help to like start computing when you just basically just make up data where it's like you don't really have that much let's say correlative features to actually give you significantly or like what would be let's say what's the word I'm looking for, data that's reflective of the actual like of the actual distribution of like the variables of it. So you basically just want to like if it's around like 60%. So I would even take out data that's like 55% missing. So you would like remove these over here. That's what we do. We drop sewage O count, we drop sewage L count. Again, if you don't remember, that's like basically sewage O is just sewage odor and sewage L is just sewage leaks. Anyways, going forward, we're just gonna drop these guys, and this is how our data set looks now. We remove those two columns, so it's a little smaller, but at least we just have the data that's like has the least amount of missing missing rows or whatever, missing values. Anyways, going forward, we're going to be using this count. We're going to just need this like a collections counter thing. And what this is showing you is basically cardinality of the cardinality of some of the categorical variables. So the only reason I'm showing this is that we're going to be using this in another function coming up. And so over here you can see, okay, what's like the plurality of like which variable or which let's say individual let's say not category, like the individual categories within our data set of let's say UHF neighborhoods, UHF 42. These are just like, if you don't know what these are just like districts within New York of hospitals. So okay, we want to know like, okay, within our data set, what's like what are the UHF neighborhoods that have like, let's say, the greatest plurality in complaints about anything, and that would be this here, downtime, height, slope, and similarly you have all these other ones, so you can just see, okay, these ones have seen now like the most complaints within UHF neighborhoods. Yeah, so they're like referenced this many times, like so there's like these many of rows that reference this particular UHF neighborhood. And we're going to be basically using this sort of dictionary here, or not dictionary, sorry, but like this sort of like list of tuple values within a function to basically give us our mode values. So like we're going to get like our most frequent we're gonna see like our most frequent categorical values, our second most frequent categorical values, which is our second mode, and we're gonna see it's the frequency in terms of like, okay, how many times they actually appear, like the actual count, and we're gonna see the percent. Similarly, we're gonna do that for like the second mode as well. We're gonna see like what is that second mode and what is the percent within the data set. And this again just shows us like the plurality of these particular categorical features and everything, or categorical values. But yes, we're going to run this. And so this is going to tell us about the quality of our category. So we have 0 missing, which is like, yeah, that's, I guess. And we have 43 UHF neighborhoods. This is what's shown in our data. So if you actually go on like online, you'll see 42. Like if you actually search up like NYC UHF 42, you'll find like 42 neighborhoods. But I think there is some sort of extra district. So we have 43. That's what was in our data set. And so again, we see that downtown height slope is our most has the plurality of of rows within that category of UHF 42 neighborhoods. And second place would come in with over here Sheephead Bay. But you do notice that like the mode percent is like 2.68 and over here is 2.48. So it's like these aren't like strong majorities of our data set. So it does seem like our data set is really like I guess what you can say fairly distributed in the amount of like individual categories that there are within UHF neighborhood. Over here we have 5 boroughs. That's true. Like New York has 5 boroughs, and our most frequently complained about borough is Manhattan. And you can see it has like 316 complaints. 136 complaints, and it has like a mode percent of 26.05, which just show that like it is a good chunk of the actual complaints within our complaint data sets. Similarly, Brooklyn, they're also 25%. So like these two take up like half of the complaints. So you see these are like the trouble areas when it comes to, let's say, indoor air complaints, as we have over here in our data set. You know, this is basically things that would happen indoor, like asbestos, gases, mold, dust, all that sort of stuff. Anyways, going forward, now we want to get to like how we're going to like treat our data. We're going to treat our data using transformations. The purpose of like using these transformations is again to sort of like get our data in a more normally distributed pattern, because a lot of algorithms, machine learning algorithms, like they work best with normally distributed data. So we're going to use so over here we make the function log transformation. It's going to log transform all of our float 64 variables, and so yeah, we're just gonna make it, and we're just gonna like see how it changes our data. We're not looking at it visually now, but we will be doing that. So over here, we can just see how it like sort of changes. The values are no longer like integer value, like actual count values that would be integer floats or whatever, but like they're just these log transform values. And similarly, we're gonna do the same thing with a square root transform. I actually find square root transforms actually like really helpful in getting your data to a more normally distributed pattern. And so we're just gonna like output it over here. And now we're actually gonna, and we have another one, it's a standardization. So yeah, we're gonna just basically see the effect of these different transformations then. And this is the last one, but it's actually like another one of my favorites, which is the clamp transformation. And the clamp transformation is gonna basically do this. So when we have like outlier values that are really like skewing our data set, the clamp transformation, which we're gonna use, it's gonna basically make those outlier values. Basically, it's going to change the value of those outlier values into some value within a range, and you want to use like a bell curve to sort of like inform what range you want to put your outlier values in to sort of make it more normally distributed. So in particular, this clamp transformation here is going to look at like values at the very extremity, very like extreme of our data set. So like the very like very low values and very like high values over here that would like skew our data, and it's going to change their value to where the plurality of data would be, or where we want it to be, which is going to be within these two. Well, basically within one standard deviation of like a mean of 0. So we're going to basically put it within like the quantile, like within the 0.34 quantile and 0.68 quantile. And so that's sort of going to make our data look more normally distributed. And it doesn't necessarily affect like the quality of our data in that like it's not like we're fudging the data, because these are only a few amount of outlier values that we're actually like clamping them down to like just like fit in with the majority of the group. So like we would use, let's say, maybe a clamp transformation first, just to get those outlier values, and then maybe do some sort of like square root or log transformation to actually like put it within some sort of normal distribution if we have some sort of like right skewed data, meaning that our tail is like towards the right. So we're going to see that visually, so it doesn't sound like just.
How did we get 0.94 and 0.03?
Oh, so these are literally I just looked over here and like went for some of the extreme value, like the more extreme value. So I went like I just went a little bit like under 0.94, but it's still like within like 1 to 2 standard deviations of like data in terms of like these are the extreme values. So similarly with like 0.03, I looked at like okay, what would be basically close to this like the more extreme values here. So it really was just like inferencing through like looking at this bell curve and looking at looking at like where my extremes would be. I'm more so looking at the extremes that are like just way off from the majority of our data. So I just chose those numbers. But in particular, when it comes to actually like making those outliers fall in line with a normally distributed, a normal distribution, you want to like put them somewhere in this middle part. So I just chose 0.34 to like 0.68, which is just like this is the percent of data that's like the percent of data that's like it's basically it's 68% is 68% of the data. So we want to just like put it within, which is like surrounds the mean, and like it's basically it's gonna like it's just going to make those outlier values have values that are within sort of like 1 standard deviation of the mean. So again, it just makes it look more normally distributed.
And in our current data, what are the outlier values?
Oh, so we're going to see that. We are going to see that. So we're just going to run this clamp transformation first. Oh, sorry. Okay, so yeah, you're not going to see which actual values got clamped. Maybe let's see. We can do here. Sorry, 10. So we can let's say up 10, and then let's also from here we do the basic complaints DF just to see like what the some of the previous values were before they got clamped. So we put 10 here. Nothing. Doesn't look like anything here. Maybe if I do like 20, let me just put like 30 just for like just to make sure. So let's see some of our some of our outlier values. Good ones here. Let's just do 13. Some of these. Sample right now. So here's a 46. Let's see. That's 19. So yeah, row 19, Bedford Stuyvesant, it was like 46, and then we like clamped it down to like an 18. This was like randomly chosen after you gave it a range. Oh, sorry. Yeah, so 19 up here, 46. So we see like 37, 46, 46. And you don't see those 46s or that. You see that 37, we don't see those 46 anymore. They got clamped to something within the majority of the data set, which is around the mean. Okay. So I don't really need this, so I'll just like delete this cell. And here I'll just turn this back to the okay. But we're actually gonna see it visually if that didn't like help out too much. So first we just want to make sure we import these, run these cells really quick. And so this is gonna be our QQ plot. Basically, like we went through the QQ plot before on week 2. Basically, it just shows how normally distributed our data is by basically visually you can see like how close it is to, let's say, a straight line, and that would like give you like an idea of whether or not this is normally distributed. This is not. You can see it has a good curve to it. This particular curve, like kind of like pushing outward towards the right, is going to be like a right skewed. Yeah, it's going to be like right skewed. So like when we see this histogram, we're going to see that its tails, like it's like thinner parts are going towards the right, and we can see that here. So we don't want that. We want something that looks normally distributed. So we can try like some of our functions. So over here, I put up over there like try the square root transformation and try like the log transformation on it and see what happens. And so y'all can try that for yourself. Make sure you like fill in, because I did leave some of these areas blank, so you guys can actually like choose your own whatever variables that you want to, or whatever feature that you want to like use. I just use species count, but you guys can like choose whatever you want. So you could use something like mole count, ventilation count, dust count, whatever. Anyways, so over here I'm gonna try the square root transformation. Yeah, I'll just go square root. We'll see what happens. You see, it looks a little bit more normally distributed. We can kind of do something better. I think if we just do, maybe if we do the log first. Yeah, if we do the log first. Let's go with log transformation. And just put another. See, oof, oh, wait, maybe do the log second, not first. Don't want that. Now it's more or less. So let's cut this. Okay, yeah, so this is, well, it's better than the last one, but it's probably best to just do the square root transformation. That seems to have gotten us the best normal like distribution. So that's something like that we may want to do when it comes to actually like preparing our data to be used in an algorithm. But we can we'll see that we can do a little bit better just going forward. Anyways, we also can visualize our data, let's say the outliers of our data based off of the bottom mystery plot. So I'm not going to run these transformations yet. I'm going to first just run the basic data frame just so you can see the outliers. Yeah, okay, so let's run this. Oops. So these are like, you can see our outliers. And also we can like look at the box on Mr. Plot, we can sort of like also see like whether or not this these different these data subsets are normally distributed. So this is particularly notable that these are categorized through like boroughs. So we're gonna look at like just looking at the asbestos counts of Queens, Brooklyn, Manhattan, Brooklyn, and Staten Island. We can sort of like look at these. We can just look at the box plot and tell whether or not it's normally distributed, whether or not like the median line is actually in the middle, and also based off of like our whiskers. If our whiskers are like similar size, we kind of say that okay, then our data is normally distributed. So these are just like easy visual ways to sort of see like whether or not your data is ready to be used in some sort of algorithm by checking if it's normally distributed. And you can see that it's not really. A lot of these seem to have some sort of skew. I'm guessing some sort of right skew just because of looking at the previous specific for transformation. It was right skewed, and it was all of our asbestos counts, and these are just like the individual like categorized into individual boroughs, but they all seem to have this sort of like long upper whisker. And so now we're gonna like apply these transformations that we previously used. And we're gonna see what happens. Like, so hopefully what we want to see is that like these whiskers become like similar size and that our median lines are actually within the middle of our box. Applying transformation clamp to make sure we get all our outliers out, and the square root transformation, which just seems like it's good to get things in a normal distribution. Let's see what happens. And look, yeah, our whiskers are a bit better. They're a good bit better, and we don't like have these outliers. So this is what we want. This is what we want. This is what we're going to be like. This sort of data is like a lot better for just running like certain algorithms and predictive models and all that sort of stuff. Staten Island's not doing so well, but it's whatever. It's not like it's just it's 1/5 of our data. Anyways, and also just like kind of as a bonus, like we have imputations. So imputations just be like, if we have some sort of like NaN values within our data set, we can just change those NaN values to like means, we can choose them into medians, modes, and also I made this function here called rand imputation. Sort of does the same thing as the clamp transformation, except for just like, it doesn't really like clamp outliers, it just sort of like, like fills in NaN values with random values within that sort of distribution, within that like 1 standard deviation of the mean, which again is going to help our data look more normalized. And given that like just remember that like, it's just like we're doing this given that our data does not have roughly 60% missing. Remember, we dropped those, so even the data that we still have only has like max 10% missing. So we're not like fudging our data like in any sort of like, really bad way. All right, so yeah, you could sort of like, if you just want to like run these functions just to see what happens, you can do that just to see like what sort of interpolation, like these are just some like interpolating functions that you can use to sort of like basically, again, it basically fills in your NaN values. So this is a particular like, it's like a linear regression based method of filling in NaN values. So over here we have backfill. This can do like a forward fill and backfill, which is again just like filling in some NaN values with values based on the values before, the values after. These are just again just methods of impute of imputing data where we have it missing. I'm not going to be using these in particular for just to like for the final sort of, I guess, demonstration of how we can turn these the data or our individual features into normally distributed data. But I'm just going to be using the square root transformation, the clamp transformation, because of like this bottom Mr. plot shows that we had like some pretty good results with most of our data within asbestos counts. And so I'm just going to be using those two and showing you guys what happens once I apply the square root and clamp transformations to all of our data here. These are all the sort of counts that we have within our data set. And we want to get some normally distributed data. So hopefully we get most of our data normally distributed. And that seems to be the case. These are like roughly normally distributed. So like if we were to choose some features to go forward and do some machine learning stuff, we choose like these features. We might be able to work with this one here. It might need another sort of transformation, maybe an imputation of median or mean values over here. But in terms of the ones that we can be sure about, like we can just like choose these guys here definitely. But this guy, like I tried several different like transformations and like imputations for like dust counts. I didn't really help much, and I sort of messed up the other ones. And yeah, so these are sort of like some of the methods that you can use, and these are a good bulk, this is a good repertoire of methods you can use, like imputation and transformations to store just feature data, transform in a way that will really like just make things better for your machine learning algorithms, and help you to like if you're doing predictive analysis, maybe some like time series stuff or some linear regressions. This would definitely just help your models run better. Yeah, so that's pretty much it. I did include some other some other functions that were used here that you can search up, and most of the functions that we used here. Well, most of the individual like functions that we use to build our methods are within they're embedded over here. So just the divs, all that sort of stuff, and cat, merge, all that sort of stuff. So you can like look that up on your own time. But yeah, that's pretty much the end of this session for today. Yeah. Sweet. Questions? How are your guys' code running? Like, is your code running all right?
Yeah.
Okay, cool. Sweet.
Well, actually, I did have a question.
Yeah.
Did you go like all the way back up to let's see, where was it? The second cell, the one with merge CSV.
Yeah. Merge CSV.
Okay, so I have a question about the outer joint. So normally, if you do a complete outer joint, it's like a Cartesian product, right? Like it maps every tuple in the first data frame to every tuple in the second data frame, right? If it's a complete outer joint.
I don't remember.
I just remember that like you get some mutual. I was going to include a picture, but I just remember that it's the mutually exclusive data of each set, and it's joined on if they have, let's say, like some features in common. So the features in common that they have is just like the categorical variables, while all the other like float 64 values were just like mutually exclusive to like.
Oh, it's kind of like an intercheck.
Okay. Yeah, sure. I was going to include like a picture for you guys, but I decided to just skimp out on the little diagrams.
It's drawing a picture of just a highlight of that diagram. So.
Yeah.
Oh, okay.
Well, that's not that.
It says
Mutually inclusive.
I don't know, man.
No. If it's a complete outer joint, I don't think it would remove the mutual.
All right, then that article is.
Well, that's a
wrong.
full joint. That like what's it called? Is it a full?
If you want only the mutually exclusive stuff, I think that's called an anti-joint. I'm not 100% sure.
Cool.
Alrighty.
Types of joints. Types. Of joints.
Yeah, but then like inner join is the one where you only get the mutually inclusive stuff.
Yeah, so over here, just looking at this SQL joint stuff. Over here, what is this? This is what is it? Outer joint. Okay, this is an outer joint. Yeah, so this is the
Oh, wow.
yeah, this is the outer joint. This is what we basically use. Yeah, this is the picture I was gonna include, but I was just like, yeah, so it's already a lot of stuff. But yeah, I definitely didn't want to use this or else we'd like. So this is what happened initially when I started doing it. Was like you basically double count stuff. And you don't want to do that. So it's just like,
Yeah, I was
make
wondering
sure-
how you guys got around that.
Question? Something like here's something back there? No. Okay. But yeah, so that's sort of like it. You make sure you gotta use the right join so you don't like, start double counting your data, which may happen like if you use concat, you have to like be careful with it. If you just like you straight use concat and it like defaults to like this, and I used concat first and it was like 2,600 rows. I was like, yeah, that's not right. And but yeah, so I just use like an outer this sort of outer join baby here. And you should be good. Lambdas, they can become a complicated topic, but they're not like super complicated.
Ideally, if you're making a lambda function, you don't want it to actually be complex. If you make your lambda function too complex, then you should not have a lambda function. You should instead just make a
Yeah. But
They're
they
meant
just-
for like quick and dirty stuff. Basically, think of them as analogous to, I know all of you have to have at least taken CMSE 131, maybe even 132. So think of them as analogous to something like anonymous classes in Java, where you just instantiate a small class for something like a callback or whatever. It's a similar thing. You just make like a small function so that, okay, well, I just need to pass a function that like adds one to every element. We'll just do that. But if it's something that's like big and complex with a lot of different logic and stuff, you should first off make it a separate function, and also Python will make you, because lambda functions can't really have too much logic in them. So
Yeah, but I just made sure to include these links just to make sure you guys can get like, I guess, informed on like using lambdas, using reduce, or reduce, and but yeah, so we'll just go through the notebook and fiddle around some things, maybe use some different data, so the asbestos counts. Like I only use asbestos counts just because it's just convenient, just use the first thing, but maybe like dust counts, see what happens. Right. Or mold, yeah, try the mold counts. So you can still have the same sort of like a similar right skew. Oh. And it has this right skew. It's actually a lot worse. So yeah, I would like, maybe do like mold here. But yeah, I mean, you guys get the gist of what's going on here. We're just transforming it and creating some data to make sure that things get into a normal distribution after checking our analytic base tables to see what sort of data we're missing and the quality of our data, all that sort of stuff. So all this stuff just helps prepare your data for the nice fancy looking word of like machine learning models. Yeah, so you see, like it seems like all of our data, all of our working data has sort of right skew. So it's all these transformations here definitely helpful. So this is even still right skewed after doing the square root transformation, since this was a strong right skew here. But yes, I did a lot of things beyond this one. Yeah, I just don't like when. Yeah, I think if I did like the clamp thing, the clamp transformation, we could probably get rid of those extremity things. But you guys get the point. You basically have to like do a little bit of experimentation, see how you want to transform your variables. Just make sure it's sort of like a consistent thing that you do with your other variables. Yeah. After the square root. Yeah. I love you. Like when I was just like experimenting, it seemed like the Picon transformation was really good at like, helping the data get to the normal distributed form by just removing a lot of those outliers. So glad I read up on it. It's not something like too difficult and everything. So just like yeah, mess around with this stuff, so we'll see, otherwise it would have been like really bad, like all these outliers here, if we didn't do any sort of transformations. Any sort of clamping. But yeah, I hope you guys liked it. I mean, you don't have to stay here unless you got questions, but yeah, I mean, you can throw out questions or whatever. Hopefully, I can answer them.
So, I mean, we changed the year to be offset instead of to be there, right?
Excuse me, what?
We changed the data type of the year to an offset instead of that.
Yeah.
Like, why did we have to do that?
Oh, because we're not doing any sort of, we're not using that for any sort of mathematical operations. This is just basically to like categorize how many counts that we had in this year, how many counts we had that year. Like we're not using it as a we wouldn't be using it as a predictive feature. If we did, we could still use it as a categorical predictive feature, like all the counts, let's say all the trends of complaint counts that were made this year versus next year and all that sort of stuff. But we don't need it as anything like the other flip values. It's more, it kind of just groups with the other like categorical things of like, hey, this is your neighborhood, this is your borough, this is your year. But then all these other ones are like, if we wanted to predict, let's say, so I use this data to predict asthma rates. And so we used basically like these three as like categorical variables that were sort of like just basically grouping our data and then seeing how our data changed year by year. But we use like these features as like actual predictors for I mean, sort of like, I guess it depends on, let's say, if you see a correlation between, let's say, if you saw some correlation with let's say year and maybe like, yeah, counts of complaints in terms of like air quality, then you can use it as a predictive feature. But yeah, we just didn't use it over here, and it's not something like, it's not like our point of focus. Our point of focus is just seeing complaints. It's not like we're not focused on years and everything, that sort of stuff. But yeah, I hope that was a good enough explanation. But yeah, any other questions? Great. Two left, really, yeah, two. Yeah, it's almost time for LDR, right? They're gonna get to it.
I assume so. I don't know.
Okay.
I mean, I'll say this, we're technically done, right?
Yeah.
So you guys can stick around for questions if you'd like. We're gonna go ahead and end the Zoom meeting and everything. Otherwise, feel free to get to class or whatever. But yeah, thank you guys for coming, and after spring break, we're gonna get started on the machine learning part of this club. So we'll start talking about introduction to machine learning pipelines and talking about, the whole general ethos behind how machine learning problems are set up and how they're designed to work. But yeah, that's the gist of it. Thank you all for coming, and see you later. Have fun spring break.
Yeah.